In this lecture, we will discuss about rate of production and decomposition. Let us consider a general reaction. Let us say this reaction is happening in aqueous phase and volume of solution is V. And the volume of solution remains constant. So V remains constant. This means if some moles of B is generated or some moles of A is decomposed, volume of solution is not changing much. So we can assume volume remains constant. Let us say we have initially moles of A that is given. So moles of A, this is A, and initially we have 0 moles of B. So this is at T is equals to 0. After some time, let us say X mole of A has decomposed. So M mole of A gives N mole of B. So X mole will give N by M into X. Let us say rate constant for this reaction is K. We can write rate for this reaction either in terms of decomposition of A or in terms of production of B. Minus for decomposition and plus for production. Let us say this reaction is a first order kinetics. So we can write minus 1 by m dA by dt is equals to K times concentration of A. Or we can write dA by A now we can integrate this equation. T is equals to 0. We have only moles of A, that is A. So concentration is A by V. T is equals to T, moles is A minus X. So concentration is mole by volume. So from here we can write moles of A, that is A minus X, is equals to e to the power minus mkt into A. So this is moles of A at time t. A into e to the power minus m into k into t. Similarly, we can find moles of B at any time t, and this is equals to m by n into x, n by m into x. So basically from this equation we can calculate the value of x. So from 1, A minus x is equals to, so from here we can write x So moles of B is N by M into X. X is A into. So now we know moles of A at any time t. So moles of A at any time t, this is equals to A into e to the power minus mkt. Moles of B at any time t, this is N by M into 1 minus e to the power minus mkt. Now we can plot a graph between mole versus time. So let us say on x-axis we have moles of A, or we can have moles of B. Now you see t is equals to 0, moles of A is A. So if I plot for this equation, t is equals to 0, moles of A is A. So we will have somewhere here. So let us say this value is here. As time goes, moles of A will decrease. So we will have something, this kind of curve. So this value is A. This is for moles of A as a function of time. Similarly, we can find moles of B. At t is equals to 0, this value is 0, so this is 1. So moles of B at t is equals to 0 is 0. Now t is equals to infinite, this will be 0. So this will be N by M into A. So t tends to infinite, moles of B tends to N by M into A. Now if I assume M is greater than N, so then final value will have somewhere less than A. So at this point, concentration we have N by M into A. Now when time tends to infinite, concentration of B tends to N by M into A. So we will have something this kind of curve. So this is for moles of B. We can have a special case when N is equals to M is equals to 1. In that case, we will have, so this is A, this is for decomposition of A, that is moles of A, and this is for moles of B, that is production. So this side we have moles of A or moles of B. On x-axis we have time. At this point, we have both concentration are equal, that is moles of A is equals to moles of B. We can also find corresponding time by equating two equations, that is moles of A is equals to moles of B. In that case we can find time. So this lecture illustrates rate of decomposition and rate of production. So this is production and this is decomposition. So I have for A case of decomposition, and for B we have case of production.